Transportation. My name is Leming Wang, and I will be your moderator for today's seminar. Okay, our Friday transportation seminar has been a tradition since the year of 2000. These seminars are usually held live on Portland State's urban campus, located on the ancestral homeland of Monoma, Kathlamet, and Clackamas, Tumwater, and Walala bands of the Chinook, the Tualatin, Kalapuya, and many other indigenous nations of the Columbia River. It is important to acknowledge that we are here because of the sacrifices first only indigenous ancestors of this place. Remember these communities and to honor their legacies, lives, and destinies. Today, we're very pleased to have Jason Anderson and Sirisha Kothuri presenting reducing motor vehicle bicycle conflict at the controlled intersections. Jason C. Anderson is a senior research associate and adjunct instructor at Portland State University. Dr. Anderson's expertise is in data analytics with an emphasis on transportation safety, travel behavior, big data, and transportation policy. Dr. Sirisha Kothuri is a senior research associate in the Department of Civil and Environmental Engineering at Portland State University. Dr. Kothuri's primary research interests are in the area of multimodal traffic operation, bicycle pedestrian counting, and safety. Here are some information about our upcoming seminars. And for those of you who are PSU students, STEP is a community of students passionate about shaping safer, smarter, and more connected transportation systems and brings together students from across several disciplines for guest speakers, field trips, and other events. STEP is open to all current PSU students, and they're excited to meet more students interested in transportation. Check them out and join them one of their events. And as for an overview of today's seminar, you can expect our speakers to present for about 45 minutes, followed by a Q&A. For those of you online, we will be receiving questions through the Q&A features on your Zoom control panel. If we run out of time for all your questions, we will give our speakers the opportunity to email written responses for any questions left unanswered. We have enabled closed captioning, but you must click on the CC feature to view them. I will be recording today's seminar. It will be available on our website later today, along with the presentation slides. If you're tracking professional development hours, this seminar is eligible for 1 hour of continuing education credit. Please sign in at front. For those of you in the room, I will pass around the sign-in sheets that you can get credits for attending today. With that, I will hand over to Jason and Sirisha.
Great. Thanks, Li Ming, for that introduction, and good morning, good afternoon, everyone. So today, Jason and I are really excited to be presenting on the study that we did for the National Cooperative Highway Research Program, NCHRP 15-73, which is design options to reduce turning motor vehicle bicycle conflicts at controlled intersections. So this is the general outline of our talk today. We'll briefly introduce our research team, talk about the motivation behind this study, go over the site selection, methods and results, and then conclusions and recommendations, and then talk about the decision tool, which was the main output of this study. So a little bit about our research team. This is a huge project, and it was led by Christina Fink from Tool Design. In addition to Tool, we also had our colleagues from Oregon State University, led by David Hurwitz, State Street's Research and Consulting, led by Rebecca Sanders. And here at Portland State University, our team was led by Chris Monsieur. And in addition to Jason and myself, we also had Nathan McNeil on our team. So the motivation behind this study is that bicycle fatalities have been increasing over the last decade. So according to NHTSA, the average annual bicycle fatalities have risen from 670 per year between 2007 to 2011 to 890 between 2017 and 2021. The most recent statistics from 2023 show an upwards of 1,100 bicyclists killed in traffic crashes. So analysis of the crash data shows that 70% of these fatalities occurred in urban areas and 31% occurred at intersections. So to respond to this, states and agencies are looking for ways and means, trying to establish policies and practices to improve bicyclist safety and reduce these fatalities. And so that is the motivation for this study. So our research objective here was to develop guidance and tools for transportation practitioners that they could use to then reduce these turning vehicle bicycle conflicts at controlled intersections. And key to this is that we really wanted to understand the relative safety performance of these intersection treatments that we're employing at the intersections. This research is specifically going to focus on a few high-level choices. So we're going to look at 5 design treatments that I'll be talking about in just a second. But we are also focusing on one specific crash type, which is either the right hook or the left hook crashes. So this crash occurs when a bicyclist is going straight and the turning vehicle is turning right, either right in front of the bicyclist or behind the bicyclist. So here are the treatments that we specifically focused in this study, and these were chosen based on a scan of the literature as well as interviews with practitioners, which we conducted early in the project. So we have 5 different intersection treatments that we evaluated in the study. The first is a conventional bike lane. So in this, the bike lane is curb tight, so it's in between the curb and a straight through and right turn lane. Through the intersection, there may be some pavement markings to indicate the path that bicyclists should take. And so the conflict area for this design type is right here at the intersection. The second treatment that we looked at is the separated bike lane. The separation mainly occurs in the bikeway segment of the facility. It may not always lead up to the intersection. And the separation is generally through the use of vertical elements like posts, etc. Through the intersection itself, this treatment behaves very similar to the conventional bike lane. And so the separation is mainly on the segment. The third treatment type that we looked at is the pocket keyhole bike lane. And in this treatment, the bicyclists are shifted left. So there's a lateral shift that takes place, and the bike lane is between the right turn lane for the motorist and the through lane for the motorist. In this situation, the conflict area is upstream of the intersection because this is the place where the motorists are turning right to get into this right turn lane, and the bicyclists at the same time are shifting left to continue into the bike lane. Another treatment type that we looked at was the mixing zone. And in this treatment type, bicyclists and motor vehicles have to share this common space. And in this treatment also, the conflict areas upstream of the intersection. So at this point where the motorists are moving to the right to enter this common space, and the bicyclists are continuing straight. And the final treatment type that we looked at is the protected intersection. So the protected intersection has many elements. There is this separation that's right through the intersection, and the separation is much more robust generally than the separated bike lane. We also have enhanced crossing, enhanced curbs, and other elements. So these are the 5 treatment types that we typically focused on. And just to reiterate, again, we are focusing on the treatments at the signalized intersections itself, and we did not focus on the bikeway facility upstream of the intersection. So here's a quick overview of all the research tasks that we undertook in this study. We started off with a macro crash analysis and then moved into a micro crash analysis. And actually prior to that, we did the state of practice and a literature review scan. Then from the micro crash analysis, we looked at selecting sites for a video-based conflict analysis, and these 2 tasks fed into our site selection. And then we also did a human factor study using the driving simulator. So here's a quick overview of this mixed methods approach. And this approach was undertaken because each of these experiments have some gaps. And so by conducting these different experiments separately and then synthesizing the results together, we thought we could address those gaps with each of the methods. So as I mentioned, we first conducted a macro crash analysis, and that is looking at crash data from the entire state. So we looked at 3 states, Texas, Minnesota, and California, and then looked at aggregate bicycle safety, trying to understand the factors that affect safety. From that, we were able to select some sites for the micro crash analysis. So we ended up with 573 sites. And these are all sites that have these bike facilities of interest that I just talked about. We had 233 crashes that we evaluated at these locations. The strength of the micro crash analysis and crash analysis in general is that it is a direct measure of safety. But the disadvantages are it always tends to be reactive because crash data is available after a year or 2. And then we also have limited information about crashes themselves, and there are variations in the crash reporting databases itself. From the micro crash analysis, we were further able to select 28 sites, and these were spread across the 5 treatment types that I talked about. We contracted with a vendor to record video at each of these sites, and we ended up with over 2,000 hours of video that was analyzed, and that led to 16,000 conflicts. And the idea with the conflict analysis is that conflicts are more common than crashes, and by evaluating conflicts, we can be more proactive about undertaking any safety measures or implementations. The disadvantages with this analysis is that the conflicts with vulnerable road users are harder to define consistently with metrics. Different studies have used different thresholds, and there is still a gap in correlation with crashes. So does every conflict lead to one crash, or one what does that relationship look like? And then the final experiment was a human factor study, which was conducted in a driving simulator at Oregon State University. That experiment had 40 participants, and they designed a course that the participants can drive on. So the advantages of this is that it's a controlled experiment. So we are able to control what the drivers see. And we can also test features in the simulator that are already not present in the field. The limitations, of course, are that it's a small sample, and then there is a little challenge with translating performance measures to safety and design decisions. And there is a limit on how many variables you can explore. So moving on to the site selection, as I mentioned, we looked at the macro crash analysis, and selected or primarily looked at facilities with primary or secondary classifications. This is in the OpenStreetMaps. And what the macro crash analysis showed us was there are a number of bicycle crashes that were also occurring at the intersection of these primary and secondary facilities with tertiary facilities. So tertiary facilities are your local and collector streets. So we added those back in and then looked specifically at intersections to select our locations that had a bikeway or treatment of interest, and that was signalized. And from that, we ended up selecting our micro crash analysis sites and also our sites for the video conflict analysis. And just due to interest of time today, we are primarily going to focus on the video conflict analysis that Jason will be talking about in a few minutes. But for that itself, we wanted those sites to be as geographically dispersed as possible, right? We don't want to just select sites from one city or one area. We want to understand how these treatments are performing everywhere. We were aiming to select 5 to 6 locations per treatment type and have these sites with a mix of traffic volumes and intensities. We also looked at feasible camera mounting locations to make sure that these sites had necessary infrastructure to mount cameras and that they had adequate bicycle volumes, because ultimately we're studying conflicts and we need enough volumes to study that. So we ended up selecting 4 cities, Austin, Minneapolis, New York City, and Seattle. And you can see that these cities are like fairly geographically dispersed. We selected these cities because they had the bikeways and the treatments of interest for us. But more importantly, they also had some sort of exposure data that we needed for the crash analysis. So here is the table of the sites that we ended up selecting. So for most of the treatments, we ended up with 5 sites, but we intentionally over-selected the offset and protected intersections because there was very little research at that time on this type of treatment. So we wanted to understand it more. And these sites were again spread across different cities. And so a little bit of the methods. So as I said, we'll be focusing on the video-based conflict analysis today. We contracted with a vendor to collect the video data and then contracted with another vendor to perform an automated analysis of the video data. And this analysis gave us the ability to look at detailed trajectories and other information. So the video data was collected over 3 months between August and October of 2022. And we made an effort to collect at least 60 hours of data at each location. There are a couple of exceptions where we didn't quite meet that threshold, and that was because of equipment malfunction. And so here are some screenshots of the camera setups and locations at the different sites. So, So here in Seattle, this is a conventional bike lane right here. In Minneapolis, this is a pocket bike lane. So in the middle between that right turn lane and the through lane. In Austin, we have a separated bike lane. This is a protected intersection, and here's a mixing zone from New York City. So just a little preview of the different kinds of sites that you're seeing. So here is the information that we got from the automated analysis. We were able to get trajectories for each road user that was extracted from the camera. And in addition to these trajectories, we also were able to know what type of road user was arriving at that conflict area. So we drew the conflict area that we were interested in, which user arrived first, We also know what the median and conflict speed of the two users are that were involved in the conflict, the type of conflict, and observed PET. PET stands for post-encroachment time. It is a surrogate safety measure that essentially refers to the time difference between when the first user leaves the conflict area and the second user enters that conflict area. So it's essentially telling you how close the two users are in time and space. So, okay, with that, I'm just going to pass it over to Jason to talk about the data and methods.
Thanks, Sirisha. So the first thing that we had to do when we received the data from the third-party vendor was do some data massaging, some data cleaning, and some data preparation. So we originally got data that included all PETs less than 10 seconds. We filtered that to represent PET of less than or equal to 5 seconds. So Sirisha mentioned that there's not much consistency, or there wasn't much consistency with certain thresholds. A recent study that just came out has summarized about 12 different studies and has come to establish with some level of confidence that this 5 seconds is a good threshold in terms of anything less than that represents some level of severity of conflict between motor vehicles and vulnerable road users. So after filtering that, we looked at some different removals as well. So any violation, so if the facility wasn't being used correctly by the cyclist or by the motorist, any pedestrian vehicle conflicts or unknown vulnerable road user conflicts were removed. Any bicycle to bicycle conflict was removed, and then any erroneous speed was removed as well. We had a couple of speeds in there that were in the 180 to 190 mile per hour range for both the motor vehicle and the cyclist, completely unrealistic for these types of intersections. And then lastly, we removed any duplicates. And if you notice here, the duplicates is almost the exact same number as the number of observations remaining for analysis. We suspect that when we extracted and downloaded the data, that the observations were simply duplicated. And so in the end, that gave us about 15,600 observations that represented through bicycle movements with vehicle turning in the same direction, so those right hook movements. And then about 550 observations in which the bicycle was having a through movement and then the vehicle was turning from the opposing direction, so those left turn movement. Next, we needed to define our conflict threshold and severity threshold. So in general, lower PET values indicate a more severe conflict, or the interaction between the cyclist and the motor vehicle is closer. However, PET alone may not be sufficient when we're trying to describe a conflict in its full detail. And so we can further inform that interaction if we can consider vehicle speed at the time of conflict. That was, fortunately for us, some of the information that was provided from the third-party vendor. And so we first defined our PET thresholds based here. Again, now some well-known and established thresholds for PET. Less than or equal to 1.5 seconds is a high severity conflict. 1.5 seconds to 3.5 seconds is a medium severity conflict. And then 3.5 seconds to 5 seconds, a low severity conflict. In addition to that, we empirically looked at what were the speeds at the time of conflict. We used median speed and then compared that to what other studies had done across the country at different locations, different facility types, so unsignalized intersections, mid-block crossings, just to get an understanding of what that speed threshold was that was used. And pretty consistently, it was in the 9 to 10 mile per hour range, which matched up with our empirical values as well. And so our speed threshold to determine whether there was high speed or low speed, that threshold was 9 miles per hour. And so what we're going to focus on primarily today are the high severity conflicts that are associated with high vehicle speed at the point of conflict, particularly for the modeling, which we'll talk about a little bit later. So for the results, I want to paint sort of this like wide brush over the results. And then Sirisha will jump back in and conclude what are the key findings from there and how can they be used in the design tool. So here is an overview of the total number of conflicts. Note that these are all conflicts less than 5 seconds, not high severity conflicts. And I'm sure most of you are immediately noticing the very large values that correspond to New York City, particularly for our mixing zone and our protected intersection treatment types. This was something that we had to deal with, and in the modeling, we accounted for this through certain techniques. There's just an overrepresentation. There's more folks, there's more people, there's more bicycle volume. Overall, there's more conflicts in New York City. Here we see mean hourly exposure. So the left side of the plot shows this by our treatment type, and the right plot shows this by our city. And so you'll notice that the light green bars represent through bicycles, and the dark green bars represent turning vehicles on approach, so that right turn movement. And we see the overrepresentation in terms of bicycle volume at these particular treatment types, mixing zone and protected intersection, as those are primarily located in New York City. And then we see also over here in New York City, a much higher mean hourly exposure rate compared to the other cities. For treatment size outside of that, it's fairly comparable with some higher volumes and separated bike lanes. For the vehicle turning movements, fairly comparable across treatment types as well. Same for city. Next, we looked at total number of conflicts, again, not high severity, just conflicts less than 5 seconds, by treatment type and by user arrival. So did the vehicle arrive first or did the bicycle arrive first? So as we would expect, again, because mixing zones and protected intersections were the treatment types from New York City, we're always going to see a higher proportion and a higher value of conflicts within those treatment types. And so we would expect this. From the vehicle arriving first perspective or bicycle arriving first perspective, there's some trends that we can point out here. With the exception of mixing zone and protected intersection, notice that a higher proportion at varying levels of split, the bicycle arrived first. This ranges from 60-30 or 60-40, excuse me, to 70-30. And then we look at the mixing zone and protected intersection, a higher proportion of conflicts occurred when the vehicle arrived first versus the bicycle. And those splits are 50-50 at protected intersections and about 60-40 at mixing zones. Well, what happens if we look now only at high severity conflicts? So those PETs less than or equal to 1 second. We wouldn't expect much difference here, just simply because of the overrepresentation of the number of observations and conflicts that we have in New York City, hence mixing zone and protected intersections. But we do see some different behavior in terms of when the vehicle arrived first or when the bicycle arrived first. So it's almost the opposite for the 3 treatment types that aren't mixing zone and protected intersections. Now we see that the vehicle arrived first, excuse me, for a couple of those, and the split is much larger than what we looked at for just all conflicts less than 5 seconds. And this is true for all treatment types. Next, we assessed the mean speed at conflict point by location and treatment type. And so there's a lot going on here. I just want to point out 3 things that sort of pop off the slide for me. The first is the pocket or keyhole bike lane, and we denote the 3 letters here represent protected intersection, mixing zone, separated bike lane, and so forth. We see that the keyhole or pocket bike lane has the highest mean speed across its locations at the point of conflict. And if we go to the protected intersection and the mixing zones, with the exception of this, outlier in Austin, these 2 treatment types have the lowest average speed at point of conflict. We're starting to see a trend now in terms of what treatments may be preferred versus those treatments that have a lower safety performance. We also looked at overall mean speed per the protected intersection, so not at the site level, as well as 85th percentile speed at the point of conflict. And again, the same trends we're observing here. So the pocket bike lane, by a decent amount, the highest average speed at the point of conflict, as well as the highest 85th percentile speed at the point of conflict, and then protected intersections and mixing zones, the lowest average speed at the point of conflict and the lowest 85th percentile speed at the point of conflict. This plot I particularly like. So this shows the difference severities of PET by these different, we have the red circles, the blue triangles, and the green squares. And so what we would expect to see is this sort of funneling effect. So fewer high severity conflicts, more medium severity conflicts to the most conflicts being those low severity conflicts. And that's the behavior that we observe mostly across these different treatment types. We can also see again how much more observations we had for those mixing zones and those protected intersections due to those locations being in New York. This also shows us how few observations relative to the other treatment types that we had for pocket bike lanes. This plot is also presents some pretty good information that sticks right out at you in terms of the proportions. It's more viewable on the computer screen and less viewable in terms of the text on the overhead projector, so apologies for that. But what we see here are these large proportions of high severity. This is now including speed. So PET less than 1.5 seconds and the vehicle speed at the point of conflict was greater than 9 miles per hour. Much larger proportions when we're looking at pocket bike lanes and conventional bike lanes compared to the other 3 treatment types. And we see that trend sort of the entire way as we go across severity all the way to the least severe, and where we see much higher proportions of the lowest severity of conflicts, meaning less than or greater than 3.5 seconds and low vehicle speed. And we're seeing those at the protected intersection mixing zones and separated bike lane. And so these descriptive statistics are starting to tell us a story again about what treatments may have better safety performance versus those that do not. But that's just a descriptive analysis. So to take this a step further, we wanted to model conflict frequency and model conflict severity. And so to do this, for conflict frequency, we considered only high severity conflicts. So those conflicts in which PET was less than or equal to 1.5, as well as vehicle speed being greater than 9 miles per hour. And then for conflict severity, we considered those different ranges of PET in conjunction with vehicle speed being greater than 9 miles per hour. Now, the premise here for this is to understand the different behaviors at the different sites for conflict frequency, as well as conflict severity. And for conflict frequency, this is something that we can use similar to a safety performance function. So think conflict performance function. And we can use that to estimate the expected number of conflicts for a given treatment type. So we can use it in safety investigation or screening processes. So you heard me say that we separate or did a various number of models for each treatment type. The idea behind that was our assumption was that the behavior of conflicts at those different treatment types was going to be different. And so instead of including everything in a single model and including maybe treatment type indicators, for example, we created 5 different models, one for each treatment type, and then conducted what's called a transferability test. The transferability test indicated to us that we indeed should have separate models for each treatment type. I'm not going to go too far down the modeling rabbit hole, but if that's a conversation that you'd like to have, or you're online, feel free to ask those questions or reach out, or we can chat after today's presentation. So the first thing we assessed is what is the performance of those conflict performance functions. And so what you see in front of you are called cumulative residual plots. And this is a really quick, easy, nice way to assess how well your performance function is doing over the range of, in this case, conflicts. And so we have this black line, which is called the cumulative residual line, and we want that to oscillate about 0 and stay within those red lines, where those red lines represent the 95th percent confidence interval. And you see that's essentially the behavior that we're seeing, with some few exceptions at those higher values. So this tells us, just by looking at this, that the conflict performance functions are performing pretty well across all ranges of conflicts. So this gives us some confidence when we go to use those performance functions to estimate or predict the number of conflicts at the various treatment types. And here's an example of using those conflict performance functions to develop predicted conflicts, or the expected number of conflicts. And so there's a lot going on here. On the next slide, I'm going to focus on just one case scenario. But you can see that as the general trend for each of the treatment types is that as the number of bicycles gets higher, that rate of conflict frequency starts to become exponential. So let's take a look simply at 50 bicycles per hour with just these different turning movement vehicles per hour. And we can immediately see that based on our conflict performance functions, the worst performing treatment type in terms of safety, conflict frequency, is the pocket bike lane, followed by the conventional bike lane. And we can extend this to look at different varying turning volumes, different number of bicycles per hour, depending on what the need of the site or the need of the safety investigation is. And then this plot here shows how much of a contributor or how much exposure means to explaining conflict frequency in terms of predicting or the expected number of conflicts. As we can see here, bicycle volume, the further away the green line is from this horizontal line, the higher the effect that exposure characteristic has on explaining conflict frequency. And again, this follows all the trends that we've seen thus far. Much higher effect for pocket bike lanes and conventional bike lanes compared to the other three treatment types. The last part of the modeling I want to talk about before I summarize this up and throw it back over to Sirisha is the severity type. So there's a lot going on here, but what I mostly want to point out is that if the sign is negative, it means that there's a lower probability of a high severity conflict. If the marginal effect here is positive, it means that there's a higher probability of a high severity conflict. And so really what we're seeing here is, with the exception of separated bike lanes with larger vehicles and pocket bike lanes with when the vehicle arrived first, overall, we're expecting a higher probability of a higher severity conflict when a larger vehicle is involved or when the vehicle arrives first, which we would expect. So in the end, we can rank on various metrics. So we have some metrics from the descriptive analysis we can use, and we also have some metrics from the modeling approach that we can use to rank sites based on these different metrics. And you'll see a trend here in terms of what sites are consistently ranked at the top. And so the first one is severe conflict percentage. And so our top sites or our top treatments, are the protected intersection, the mixing zone, and the separated bike lane, each of which had a proportion of severe conflicts at 6% or less. When we look at mean speed at the point of conflict, the same three are at the top, just in a slightly different order. So we have our mixing zone, our protected intersection, and our separated bike lane, each of which have a mean speed at the point of conflict less than 10 miles per hour, while the other two higher than 10 miles per hour, and for the pocket bike lane, quite a bit higher than 10 miles per hour. And finally, using our conflict performance functions, we can estimate what the expected or what the predicted number of conflicts would be at a given treatment type. And the ranking is again the same in terms of the top three. So separated bike lane ranked first, mixing zone second, and then protected intersection third. So despite what metrics we're looking at, the same three treatment types are consistently at the top in terms of safety performance. So before I pass it back over to Sirisha, what are some other key results? I've touched on a couple of these already. Bicycle volume is a more important contributing factor to the conventional bike lane conflict frequency, as well as the pocket bike lane conflict frequency. Some sites, although not shown on here, using site level indicators, were significant in explaining both frequency and severity. We can chat about that. It's also in the report. We provide links at the end of today's presentation. If the vehicle arrived first, the conflict was more likely to be severe. And then finally, if the conflict was with a larger vehicle, the information we had was whether it was an articulated truck, a box truck, or a bus, there was a higher probability of a high severity conflict. So that wraps it up for my section. I'm going to pass it back to Sirisha to talk about the conclusions and recommendations and finish up with the decision tool.
Thanks, Jason. Okay, so what does this all mean? As I said before, we just talked about the conflict analysis today, but we had the other two experiments that we also looked at, the crash analysis as well as the simulator work. So bringing all those results together, we were able to provide some conclusions and recommendations for practitioners to consider. So first, with protected intersections, we recommend it for any location where space can be reallocated to provide a protected intersection. We did see some, the crash rates were in the middle for these three cities. Lowest crash rate in New York City. This was where we saw a lot of conflicts, as Jason mentioned, but then when you control for exposure, the crash rate is low. Similar number of conflicts as the mixing zone, and we also have the second lowest mean speed at the conflict point. Research done by others has consistently shown, with protected intersections and with separated bike lanes, that people feel most comfortable biking when there is separation. And so so these were the findings there. In terms of the separated bike lane, we recommend where there is not enough space to provide a protected intersection. We did see higher crash rates in Austin, Minneapolis, and Seattle, and second highest crash rate in New York City. The issue we think that we're seeing this is that we used exposure models, at least in the 3 cities, to estimate volumes, but we think that the exposure models are not sensitive enough to capture the effects of these new facilities in terms of increased ridership. So we think that may be causing the higher crash rate. We did see the lowest number of predicted conflicts in our conflict analysis, and then the speeds were sort of in the middle. And again, research from others has pointed to people stating that they're more comfortable biking at intersections that maintain this separation. Mixing zone, we recommend that this feature be provided only where right turn volumes are high, but there is not enough space to provide that separated bike lane at that intersection. From the data analysis, we did see low crash rates and lowest predicted number of severe conflicts. People are generally managing their interactions quite well. And then we also saw lowest mean speed at the conflict point. But again, from the literature, we see people are not comfortable when they are in these sorts of facilities when they have to share space with motor vehicles. The pocket bike lane, you saw from our the findings that Jason just presented. So this is recommended in very limited situations. We recommend a mixing zone over a pocket bike lane in most situations. We did see second lowest crash rate for this design and lower predicted number of conflicts, but we did see high vehicle speeds at the conflict point. So that gives us pause. And then people are also, again, stating they're not comfortable in these types of facilities where they have to merge and move laterally to the left. So this is just, again, reiterating the summary of the things that I just talked about. And so how does this all come together? So remember, our objective was to provide guidance for practitioners and a tool that'll help them decide which intersection treatment they need to use. So the input to this tool, so this is the flowchart right here. And the input to this tool is hourly right-turning motor vehicle volumes and existing or anticipated hourly bicycle volumes. So having these 2 pieces of information, you can work your way through the tool and figure out what the recommendation is for the type of design treatment that you should use at intersections. And again, this is just for the intersection. For the bikeway portion or the segment portion of the bikeway, there are other tools like the FHWA's Bikeway Selection Guide and more recently the AASHTO Bike Guide is also out. These can provide you information about what sort of bikeway should you use leading up to the intersection. But then the decision tool that we developed should be used then at the intersection to figure out what treatment should be used. So this decision tool, a few points about this, it's designed for the interested but concerned bicyclists. But then practitioners, always have the flexibility of choosing the design that they want. You can choose a different design depending on the local context and your judgment. The thresholds that we developed in this tool can be considered minimum. So you can go above and beyond what is recommended here to choose the particular treatment that you want. So this chart should be familiar. Jason just showed this. This is the conflict performance functions. And so this was used in developing that decision tool. And so And that's how the tool was developed. So what this research also provided is revised thresholds for phase separation. So previous research from AASHTO was that the threshold is 150 vehicles per hour. And so that's where you do the full phase separation, signalize different phases for bicyclists and motor vehicles. But based on this research, we were able to provide more precise thresholds of when you would need to consider different sorts of treatments at the intersection. Okay, and so all of this is in the design tool guide. And as Jason mentioned, here are the links to the products that came out of it, the conduct of research report, which talks about all of the research, the different experiments that was done and the results, and then the decision tool itself, which is in that other document, NCHRB report 1125. I think that's all we have, and happy to take questions.
Jason and Sirisha, for those of you viewing the seminar online, please feel free to submit your questions. Use the Q&A feature in the control panel of your Zoom window. For those of you in the room, of course, you can raise your hand and ask your question. So we'll let Jason and Sirisha pick their questions in the room.
So real quick, there was a typo on one of the slides. The pocket bike lanes had the highest number of predictive conflicts. Okay. Yes, I realized that. So I saw some folks going, what? You just said something different. So just let that be known.
I'll ask a question. You talked a lot about, or like one of your indicators that you evaluated things on was whether the motor vehicle got there first or the bicycle got there first. Could you explain like the importance of one versus the other, or just provide a little more context for that?
Let's go for it.
Okay, so there's been some research into it, and the motor vehicle arriving there before the bicyclist. So if you think about the movements, the bicyclist is going through, the motor vehicle is sort of cutting off their path. And so that can lead to a more severe conflict. Whereas if the motor vehicle is behind the bicyclist, then they see the bicyclist and they're sort of adjusting their interaction.
That makes sense.
To add on to that too, from the modeling perspective, just wanted to see, was there a significant effect versus when they arrived first versus when they didn't? And that was information that we had in the data. So we tested it to see if it had a significant effect on conflict severity.
Okay.
Going back in time a little bit to research design, I realized that panel made decisions a long time ago, so maybe jogging memory, but curious what the process was that was guiding this study decided that whether or not to use control sites. Was it determined that like non-protected, non-bike lane intersections like that had been covered well enough so that we already understood the magnitude of difference? Or, was there another reason why controls were not?
Are you specifically talking about the conflict analysis portion of it?
Yes.
Okay, yeah, no, that's a great question. We, I think, did consider it at some point. The trouble with a lot of the data is we don't always know the installation dates and things, right? And so yeah, so we did consider it, but then with budget constraints and everything, we figured, just studying conflicts at a wider variety of sites would help us see that. I don't know if you wanted to add anything to that.
Yeah, I mean, there's some current ODOT project right now where we're considering control sites. So I was brought in a little after that decision was made, so I can't really comment too much on it, but overall, I think it adds additional insight by adding control sites, right?
Yeah.
For the protected bike lanes, I guess this is just a clarifying question. The type of protection versus like posts or like a concrete barrier type, like, was that included in this analysis, like differentiating between the effectiveness of those two types?
No, so we tried to select sites that were as homogeneous as possible. And at the time the study was done, and I think even now, there are not that very many protected intersections in the US. So we're kind of limited by what we have. But yeah, no, we didn't, we tried, but yeah, we didn't consider, yeah.
Question from myself. In terms, I believe you certainly considered this is the choice for the either predicting the conflict frequency versus the conflicting rate, crash rates, conflicting rates. So what's your consideration of favoring the conflict frequency model, a count model, versus a conflict rate model where you basically divide the number of conflict by the bike volume? At least when the later part, when Sirisha talked about the crash rates, it looked like actually it might be, maybe both are interested, but at least they're really also interested in looking at the crash rates normalized by the bike volume.
Yes, I mean, I think analyzing conflict rate is, I think that's a fantastic approach to take. The reason we considered count data models and conflict frequency or conflict performance functions was to treat them as like safety performance functions. And so safety performance functions are a widely used tool to assess the safety performance of different treatment types, different segments, screening tool. And so the intent behind the conflict frequency models was to provide a tool like that, but for conflicts as opposed to crashes. I suspect that if we did a crash or a conflict rate, maybe using a Tobit model of some sorts, we'd likely see similar results with maybe some subtle differences on the exposure end, because that's the general behavior when we look at crash frequency versus crash rate. That would be my anticipated change in the results.
Well, then, what's not clear to me is because for one, you also have the distribution between different treatment type is very different from different cities, very different, right? So kind of normalize those by bike volume. I'm curious whether that will make a difference in terms of the model results. But thanks for the question. If there are more questions.
Yeah.
Just a clarifying question, but with getting all of the sites sort of homogeneous, was this typical speed of the cars already at the intersections considered, and also the lighting conditions?
Yeah, we undertook like a huge data collection, pre-data collection process. We had big spreadsheets of like students go through the Google Street View images, and then also mine data collecting like the AADT annual average daily traffic, speed limits, number of lanes on the cross street, the conditions at the intersection. Yes, we did look at that. Yeah.
So process question, I've did many years ago a number of these conflict analyses, and they were mind-numbingly boring because you just over and over and over watch a video. Oh, this is level 2, and it is the absolute worst way for a graduate student to make a living. Is that still what we're doing, or have we priced them out with AI at this point? Is there, did you use AI? Is there potential to do that?
Depends on budget.
Yeah.
Increase your sample size?
Yeah, short answer, depends on budget. Yes, there are tools. We did use an automated tool. So there are vendors that do that with AI. And so, yeah, we did not have any graduate students watch video. That would be too much for this scale of study. So yes, there are tools, but yeah, we do still occasionally do projects which have manual data collection. So And there are a number of like open source tools that are out there, like the YOLOs, working on a study right now that's trying to adapt YOLO to automatically detect pedestrians and bicyclists. So yeah, I think that space is constantly evolving. I think we will see the automated tools used more and more in AI, but cost is still a consideration. The budgets sort of dictate, which approach to take.
Okay, I'll ask a few online questions. So the question here is there a way to link the surrogate safety indicator to actually crash risk or severity outcome? And how did you come up with the definition of the level of conflict severity using PET and vehicle median speed and those thresholds, so severity and on PET?
I can take the first question
Oh,
and you want to take the
sounds
second.
good.
Okay. So the first question was, how is there a link, right, between crashes and conflicts? I think I spoke about that earlier. There are a few studies that have looked at the link between or correlation between crashes and conflicts. I will say it's not conclusive yet. We definitely need more research on it. Right now, I'm working on a study with ODOT to actually answer that same question, trying to compare the crash and conflict risk. So yeah, especially on the vulnerable road user side, I don't think we have conclusively answered that question.
And we did do a, excuse me, a basic comparison between crash counts and conflict in this study, so
Yeah.
you can view some of those results if you follow the link. I would also just add, some of it depends on what surrogate safety measure you're using too, in terms of how well crashes correlate with conflicts. In regards to the thresholds, that was overall the question, right? So let's do the PET thresholds first and then the vehicle thresholds. So the PET thresholds, as I mentioned, those currently, based on a recent study, are fairly well established in terms of once we get below 5 seconds, those are conflicts that we should be concerned about. And then the differencing or the varying levels of severity between that are pretty agreed upon using different methods at different locations. So from empirical evaluations to simulation-based techniques, from controlled signalized intersections to mid-block crossings, it's fairly consistent across all of these varying factors. And so we feel really comfortable in choosing those PET thresholds. From the vehicle speed side, it's similar, albeit there's less work or less studies that use vehicle speed in conjunction with PET. And so we looked at what our vehicle speed distribution was at the point of conflict, assessed some descriptive statistics, median, 85th percentile, so forth, and then compared to the few studies that have used vehicle speed, our results were consistent with their results, and therefore we moved forward with selecting that 9 miles per hour as our vehicle speed threshold.
I just want to add that there are studies which have looked at just using PET as a measure of conflict severity, but then you will have people sit down and review those conflicts and then say, is this a conflict or not, right? Sometimes the interactions that are still less than 1.5 seconds, you can view it and say, that seems safe because people are aware of each other and they're moving at a slow speed. So we wanted to take that manual viewing and processing of conflicts out of the equation. And so adding speed, we thought was one way to do that.
Second online question, there is a large variety of designs for mixing zones, and many jurisdictions simply end the bike lanes at a conventional right turn lane with no marking indicating for motorists that cyclists may be present. Did the mixing zone in the study have a consistent design? And if so, did they always indicate to motorists and cyclists may be present? If not, are there any attempt to differentiate between those different type of mixing zones?
Yeah, I think we were aware that at least in New York City, there were two generations of mixing zone. There was a longer mixing zone in the beginning, and then they went to a much shorter mixing zone as closer to the intersection. And as I said, we tried our best to keep it as homogeneous as possible. I think there's more details definitely in the report on the sites themselves and the detailed characteristics, I will say, of the mixing zones. I can't quite remember off the top of my head whether there were markings for each, but I think there were.
Great. Actually, another question about PET. Can you explain in layman's term what is a PET?
You're better at that.
So PET stands for post encroachment time. So it is basically the time difference between when one user leaves the conflict area and the second user enters the conflict area. So it requires for someone to define what that conflict area is. And it could be where those trajectories are kind of coming close together, if you think about it from the trajectory way. So it's just a difference in time when two users will be occupying the same space.
Are there more questions in the room? I will continue. It's a lot more online questions. In the case, of course, you're talking about the design decision tool and design guidelines. So in the case when budget is a constraint, when most city cannot redesign at least many of their intersections, what will be one change that I think will make a biggest impact on safety for cyclists?
I think that's a tough question to answer. It depends on context, obviously, but I think from past research, from our interviews with practitioners and other studies, we know that separation is key. So separating the cyclists from motor vehicles, I think would be beneficial to improving safety.
We are at that time. Let me ask one last question. Maybe I will ask this one here. So in your site selection, your indicate, I do not know whether this is a fact. Florida consistently ranks at near the top of bike and pedestrian death. Have you considered maybe include probably looking at other factor data availability? Any consideration of cities from Florida?
I think that's a good question. When we did our wide scan for cities and facilities at the time, so we were looking at this geographic diversity. We were looking at places which had data. So the reason we picked those 4 cities is there's some level of exposure data. Bicycle volumes and counts are very difficult to find at all of these locations. From prior projects, Seattle, Minneapolis, and Austin had exposure models that we could use. New York City, we were able to find some short-term counts, which we were then able to extrapolate. So yeah, I think it would be great to consider other places and cities, but we need that exposure data, and that was sort of a limiting factor.
And the cities also have to have some level of like implementation of the
Right.
design treatments too.
Great, okay, thank you all for attending today's Friday Transportation Seminar. For those of you who join us remotely, after the seminar ends, you will have the opportunity to complete a brief survey about today's events. It should only take a few minutes, and we will appreciate your feedback. With that, thanks, Jason and Sirisha again. Thank you all for joining us today.
Happy holidays.